Hello, everyone. My name is Vladimir Skavish from Bank of Canada. And today, Sophia, Sam, and I will tell you how we're using a quantum annealer to solve complex problems in economics. Specifically, we'll be finding stable networks and stable cycles in cryptocurrency payment networks. Before I proceed, I'd like to say that the views expressed in this talk are those from the authors and not part of Bank of Canada orthodoxy. Sophia and I will start by giving you the motivation behind the project, why it is we're looking at this and what we're trying to achieve. Then Sophia will present you the economics model, and Sam will give you the quantum implementation of this problem. And this team is this project is a collaboration between Multiverse and Bank of Canada. I don't believe Bank of Canada has presented at this conference before. That's why I thought I'd introduce to you our organization and also tell you a little bit about our quantum lab for advanced analytics. Bank of Canada is Canada's central bank, and our principal role is to promote the economic and financial welfare of Canada. Our strategic plans calls on us to harness innovation to be able to achieve our goal. And we're innovating in terms of payment system design, in terms of cryptocurrency, and of course, quantum computation. The bank's quantum lab began around 2 years ago. It was a grassroots effort where some of us have realized that the quantum ecosystem has matured to the point where we might start being able to use quantum computation to start solving some of these very difficult problems in economics. Initially, it started small with a few people, but now we've got broad interest from across the institution. We've got a team that's growing. We've got several proof of concepts on the way, and today we'll present you one of these projects. Our overall goal is to, as I said, use quantum computation to make it possible for economists to solve impossible problems. And in particular, for this problem, we wish to solve a complicated economics network problem that is computationally intractable. And before we proceed forward, I'd like to make a disclaimer that the views presented in this presentation are those of the authors and not of the Bank of Canada.
Thank you, Vladimir. Hello, everyone. Let me start my part by saying that networks are ubiquitous. Actually, they're everywhere in social interaction, in financial transactions, in trade flows. Internet is a big network. So the problems that we study today, they can be applied in all kinds of areas. But I would like to use an example of cryptocurrencies in order to motivate our study today. Cryptocurrencies becomes widely used, but they are still not used very often as a method of payments by firms. And so today we would like to study this question and to understand whether the adoption of cryptocurrency as a method of payment is going to happen equally, and what is going to impact that, how the networks will interact with that, and what is going to be the final outcomes? Will it be adopted at all? Will it substitute the other methods of payments and so on? So we would like to study that using a very simple model. Of course, the model doesn't capture everything, but it will provide us some insights. And if I can go to the next slide. Yep. I will show you the intuition of the model using the example with 3 nodes, which would be 3 firms. And then Sam can actually explain you whether we can expand this example to multiple nodes. So let's start. You have a network in front of you, and this is network with 3 firms, and each firm is located in a separate location, and there is a bank next to this firm, which serves it. What happens is that firms trade with each other, and they use different methods of payments depending on the type of good that they're trading. Sometimes they can use cash, sometimes they can use bank accounts, so bank transfers. And now they also have an option of adopting a Bitcoin or another cryptocurrency as a method of payment. So if they will adopt this method of payment, we will say that there is a link between them. And if they don't adopt it, then we will say that there is no link between them. So basically, we are interested in the network formation problem. Now, there are two interesting things happening. The first one is that the adoption of the cryptocurrency as a method of payment is a decision that needs to be made mutually, right? So both firms need to agree on that. And that's why we have to consider the bilateral network formation rules. There is another issue, is that the banks are also strategic. And so if the firms will adjust their methods of payment, they may impact the demand for bank services. If banks will not face enough demand for their services, then they can decrease their fees, which will again attract the firms back to the banks. So there is this issue with how much the fees will adjust. So now the firms decide on what is going to be their optimal network. And we want to know also what is going to be the equilibrium network, because the decision of one bank may not coincide with the decision of another bank. So we ask ourselves a question, what is going to be the equilibrium network, the network that will persist at the end? And we find a very interesting thing is that the equilibrium networks will not be symmetric, which means that if we start with firms being identical and all banks behaving in the same way, then we will find that the equilibrium network will be different for each bank. So it means it will not be symmetric in a sense. That, of course, doesn't always happen, but there is some set of parameters of when it is the case. And let me now introduce you briefly to the idea of how we find it. So first of all, we define something called a utility function. That is basically a function which defines the level of happiness of the firm, depending on the network structure and depending on the fees. And the fees may include the fees of setting up the cryptocurrency as a method of payment, the fees associated with the banking services, maybe also the fees associated with particular trade, particular good, and it will also include different benefits associated with using a particular channel and so on. So this is going to be an expected utility function, meaning that we allow for some randomness depending on which goods will be traded. In fact, that randomness will lead to the result that the firms will not switch to one method of payment completely. They will be using at least two methods of payments. And using this utility function, we can next define the equilibrium network, which we'll call also a stable network. The stable network is a network which is prone to deviations, which means that there is no a single firm that would like to break a link if the link exists, and there is no single firm that I would like to collaborate with other firms and supposedly they both agree and make a new connection. So now the interesting thing again is here we would like to draw your attention to this case of free stable networks which are not symmetric. So for me as an economist, it's very interesting, but I also know that the world is more complicated than that. And it would be great to know whether these results are sensitive to the networks and whether we can expand these results for the cases when we have more firms than free. So apparently this is actually very difficult. Sorry, what is the next slide? Can you go to the next slide? Yep. So apparently this is very difficult to expand it to many networks. Of course, we can go to maybe 4x4 networks, but if we go 5x5 and 6x6 networks, then the system becomes overly complicated. I hope Sam will have some time to give you the numbers. So that's where we thought that maybe quantum methodologies can give us some advantage in finding the stable networks and explaining how the cryptocurrency adoption will be developing. Thank you. Next.
Okay, thank you so much, Sophia. Oh, sorry, could I see my slides again, please? Hi, so my name is Samu Gel. I'm the CTO of Multiverse Computing, and we and the Multiverse team are really coming more from the, so we're bringing the quantum expertise and working really low level with the machine and asking this question: how can we map this very particular problem that Sophia described, and extremely complicated. I can't emphasize this enough. This has been around since the 50s, and we're still not able to efficiently solve this algorithm. So I'll just describe it in really schematic terms and try to give you a flavor of how we're going to efficiently address this problem on a quantum computer. So the question that we're trying to ask, that we're trying to answer, as Sophia said, is what's the equilibrium state of a three-player network? And the key quantity here is the utility change. So any two players are able to form a link together if they have a utility gain to doing this. And if there's a link between two players, any single player can break it. So this is analogous to the way that, for instance, Sophia and myself could enter into a commercial relationship if both of us are agreed to this and have an advantage to this, but then either of us is able to break that link between us. And the way that people would typically solve this kind of problem is by studying a super network, which is what's in the center here. So in my super network, each node corresponds to a graph configuration. So you can see my node 7 in the super network corresponds to a fully connected graph. And then the super network is directional. And this means that, so for instance, if I start from configuration number 7 over here, you can see that there's going to be an advantage either to players 3 or 2 to break the link between them. And then I wind up in this node 5 over here. And this node is stable, and you can see that because there's no allowed deviation from here. So it would be tempting to just feed the super network straight into a quantum annealer and try to find the efficient path. The problem with that is that the super network has 2 to the n squared nodes, so that it's got a super exponential number of nodes in the number of players. So our idea is, instead of mapping each node of the super network to a qubit, let's map each link between players to a qubit. And this vastly reduces the number of qubits we need. The problem is now the graph is dynamic. Okay, the graph is going to change throughout the computation. And so you can see that it's already qualitatively different from typical problems with a fixed graph like maximum independent set. And so I'll give you a flavor now of how you can solve that in D-Wave. So the idea is you start by encoding the network configuration to your QPU. So here, for instance, I'm starting from this graph over here that has connections between P1 and P3 and P3 and P2. Then you'd look at all adjacent graphs, so or deviations or single deviations from that base graph. And you'd ask, do the players collectively have an advantage to performing that deviation? And if you find that none of these deviations are allowed from the utilities point of view, then you're in a stable network. And this is so this is already telling you that and so this is the case over here, for instance. I've indicated with a cross that, for instance, P1 and P2 absolutely do not want to form a link between them because there's no utility gain to doing this. And in the same way, there's no utility gain for any players to breaking any of the existing links. The way we're going to find these on a quantum annealer is to penalize graph states that have any allowed deviations. Great. So now let's dive into the details, and I'll show you how to do this from the point of view of a single deviation. So here I'm going to ask the question of, do I want to break the link between players 1 and 3? And what I want to do is penalize the energy of my system if breaking that link is desirable. So this is the Hamiltonian this is the cost function that's going to allow me to do this. I'm not going to go through the mathematical details because it's a little bit redundant. However, all the mathematical details are at the end of these slides, and I'm more than happy to share these with you. So if you're interested in finding these out, just shoot me an email or shoot any of us an email, and I'll send you a copy of the slides. But I'll give you a taster of how this cost function works, basically. So this term C, essentially we're interested in what the change in utility for players 1 and 2 is. And so this is already telling you that I'm only interested in the sign of the change of the utility for player 1 and for player 2. And so what I'm going to do here is associate a new variable. This is an ancilla variable that I call Z1 to the sign of delta U1. And then equally, I assign a variable Z2 to the change in utility for player 2. So this is what this first term C does. The second term PR will allow me to remove a link. And I already know that I'm allowed to break a link if either player 1 or player 2 wants to break the link. And so this is already telling you that the relevant quantity for doing this is going to be a variable ZR that's an OR over variable Z1 or Z2. So this is the role the PR plays. PR just gives me this variable ZR that's an OR over Z1 or Z2. And similarly, PA gives me the condition for the addition of a link. And I know that I'm allowed to add a link if players 1 and 2 want to add this link. And so I'm going to add a new variable ZA that's simply Z1 and Z2. And then this last term D, this is where the magic really happens. Like, this is how I'm going to penalize the energy if if an allowed deviation of my graph is desirable. And to introduce this term D, I'm going to add a new ancilla, which is delta. And delta is simply going to tell me, am I trying to add a link or am I trying to remove it? And obviously, like, this is going to be dependent on my starting graph here. So for instance, between P1 and P3, there's already a link. And so I can't add an extra link. The only option I have is to remove it. And so there's going to be some constraints on the value of this delta. But the term D is simply 1 minus delta ZR and delta ZA plus delta ZA. ZA, as I said, if its value is 1, then I know that my players collectively want to add a link. And if it's 0, my players would like to remove a link. And if it's 0, my players do not want to add a link. And similarly, ZR is 1 if my players collectively want to remove a link, and it's 0 if my players would rather not remove a link and keep things as they are. And what you can see is that this term D is going to have a value of 0 if ZR and ZA are both 0. So if players are not trying to add or remove links. But if ZR or ZA are 1, then D has a positive contribution to the energy. So this corresponds to penalizing states where my players want to add or remove links. Here's the energy spectrum of the Hamiltonian. Oh, I forgot to say something very important. So this is the Hamiltonian for a single change to the graph. And then to efficiently solve this on a quantum annealer, I simply have to take the combination of all graphs with I simply take the combination of all possible graphs, and this allows me to efficiently explore the energy landscape. This is the energy landscape for this particular graph over here, which has 3 stable states, nodes 1, 2, and 4. And as you can see, these appear in the low energy parts of the spectrum. So you can see that I can find these stable states simply by sampling on my quantum annealer the low energy spectrum of this Hamiltonian. Similarly, it's possible for me to have stable cycles in my system, and this is a situation where there's no stable network, but instead my players are going to choose to oscillate between equally unstable configurations of the graph. And what's interesting in this figure is you can see that these stable cycles also appear in the low energy parts of the spectrum. To the last thing I'd like to tell you about is the bottleneck of this system. And the bottleneck is in computing this quantity C. This requires us to pre-compute all utilities. And this also has this awful, super exponential complexity. And this is limiting us at the moment to studying 4 to 5 players max. However, this system is very much a work in progress. We've never actually presented these results before. And we're currently looking at expanding this to computing the utilities on the fly in certain specific cases. And this will allow us to go up to 10 or more players. So I can't see my slides anymore. Hi.
Hi, Sam. How are you? It's Jen. I think we're almost out of time, but I wanted to get at least one question in because I know we're really trying to have conversations here. And I don't know, maybe Vladimir or Sophia, you want to answer this. The question that has come in is, how do you what advice do you have for other companies who are beginning to get started in quantum? One of the two of you want to take that?
Sure, I'll take that one. Well, if you have funds and people, go ahead and do it. If you don't have people, hire them. If you don't have funds, well, I guess work on your base model. But the time to try quantum computation is now. 5 to 10 years from now, it could be as big as quantum machine learning. I'm very optimistic about that.
Thank you, Vlad. Do you want to, Sophia? Do you want to add anything to that?
I just want to say. I just want to say that I'm an economist, so I don't have a computational background. And I think that should not be a barrier. And people should understand that it's not a barrier and scientists can talk the same language. So we've been able to understand each other, with Vladimir being physicist, Sam being a physicist with more computational power. So just don't think it's a barrier to teach people quantum computing.
That's awesome. And Sam, you have 5 seconds. What advice would you give?
I think Vladimir's team did it incredibly to form a reading group and start learning this way.
Thank you. Take care, all. Thank you so much for joining us.
Take care.